right, in college algebra today, we're looking at exponential growth and decay from section 4.6. All right, this is the exponential growth and decay formula right here. This is what we use, this equation, where A is the accumulated amount, A sub 0 is the original amount. Then we have the natural base E, then we have our K and our T, which the K is a percent of increase or decrease, and T is the time in years, or could be days or hours or whatever, but most times it's years. Your percent of increase or decrease right here, K, if it's positive, it's an increase. If it's negative, it's a decrease. And what this means is over a period of time, like our population grows, and naturally, because we have bring new babies into the world. Some people die out, but overall, our population will grow. Some places it might decay, it might decline, but we use this for those kind of cases where we're trying to see how something grows or how it withers away. Now, we also have a similar equation right here, A equals PERT, P-E-R-T. This is compound interest. It's interest compounded continuously, which we have this right here we've dealt with before. This is an equation we use for interest that's compounded quarterly or monthly or semi-annually, whatever, where N is how many times it's compounded. But this is compounded continuously, which means it's just naturally growing minute by minute, hour by hour. And we'll have some of that we'll deal with here shortly. Anyway, in this first problem here, if you look at this, the growth of bacteria makes it necessary to time date some food products so they will be sold and consumed before the bacteria count is too high. Okay, that makes sense. You own a meat store, you want to sell your meat before it goes bad, so you got to pay attention to that time date. Suppose for a certain product, the number of bacteria present is this right here. So here's an equation that shows the number of bacteria in this particular item, where T is time in days, and the value of F of T is in millions of bacteria. Find the number of bacteria present at each time. So first is 3 days. So basically all I'm going to do is right here where T is, I'm going to put 3 in there. All right, so I'm just going to get my calculator here. Okay, I'm going to do 500, and I'm going to have E to the 0.1 times, and it was 3 days, so 3, and I get 674.9, which rounds up to 675. And here's the answer right down there, so you can see we're in good shape. Same thing here, 4 days. I'm going to type it in. So I'm just going to go back to my original problem, just type a 4 over the 3, and then there you go, 745.9, which is 746. And we're looking good there too. The last one says 2 weeks, which there's 7 days in a week, so that's 14 days. So for my days up here, I'm just going to put 14. And I get 2027.59, which rounds up to 2028. And we got all 3 of those right, so we're in good shape. Number 2 is similar. In the study in the 1970s, it is found that one model of legislative turnover in the country A parliament, country A is some country, was described by this following formula. So here's our formula. Okay. Now, in this formula, M of T was the number of continuously serving members at time T. Here, T equals 0 represents 1965. T equals 1 represents 1966, and so on. All right, so 1967. Okay. Find the number of continuously serving members in 1967. So what we're going to do is, first of all, 1965, T equals 1. 1966, I'm sorry, T equals 0. t equals 1 in 1966, and then 1967, that means t equals 2. So I'm going to take 2, and I'm going to put that in the equation here for t. So here we go. Bring my calculator in. I got 403. Okay. I'm going to do my E button. And then I've got negative 0.09 times 2. And I get this over here, 336.6, which is 337. Okay, and you can see my answer down here. We're in good shape, man. We got it. B, find the number of continuously serving members in 1973. So I need 73 here. What's 1973? What does t equal for that? So basically, I just do a little subtraction. 1973 minus 1965, and I get 8. So t would have to be 8. And so I'm just going to go change my thing up here and put 8 in for t. And I get 196.1 versus 196. And we're good to go again. We got that answer. The last one says 1978, which means t would be 13. I'm just going to do 1978 minus 1965, which is 13. So t equals 13. I'll put that in for time, and I get 125. And we're good on all three of them. And you can see here how the number's declining, because see, it was a negative percent, so the numbers are declining, which is a decay. Okay. Number 3 is the same kind of problem. A sample of 600 grams of radioactive lead-210 decays to polonium-210 according to this function right here. So we've got this, where t is time in years. Find the amount of radioactive lead remaining after 4 years, 6 years, 10 years. All right, these right here, I'll let you do those because they're just like the first two problems. All right, so you're just putting that in for t. But now what I want to do is I'm going to do D here. Find the half-life. All right, for a half-life, in this equation right here, see, if you go back to our original thing here, this number right here is the original amount. The number right here in front of the E is the original amount. And you see right here, that was 600. So that's apparently what they had originally. All right, so half-life means that this, A sub t, would be 300. So I'm going to do this. Okay. And now I'm just going to solve that. So to solve that, I'm going to divide both sides by 600, which makes that cancel off. And look here, that's 1/2. Okay. And then to go from there, I'm going to divide by negative 0.032. Okay, hold on. Wait a minute. I didn't write my E down. Sorry, made a mistake. I realize that now when I got to solving there. So I screwed up. When I divide this out, now that's e to that power. Okay, so I got to get rid of my e. So I jumped the gun here, left my e. I got to do a natural log of both sides to make the e cancel. Okay, so it's natural log 1/2 equals negative 0.032t. And then I divide by negative 0.032. That cancels off. Okay, so let's see here. Natural log of 1/2 divide by negative 0.032, and I get right here 21.66. And we're good there. That's the answer, 21.66. Sorry about this right here. I didn't write my e down, and I just kept going, but it was e to this power, see? So when I divide by the 600, it's e to that power, which means I have to do a natural log to get rid of the e. All right, we'll go to 4. 4, find the doubling time of investment earning 5% interest. So we're going to go to this right here. This is a interest. All right, so A equals P e to the RT power, PERT. Okay. It says find the doubling time, which means if I started with $1, doubling would be $2. Okay, I'm just going to put those numbers in. So this A would be 2, and then P would be 1, which would just go away, and just have e to the RT, which R it says is 5%, so 0.05 T. And there's how I'm going to set it up. Okay, so again, if this is 1, then that would be 2 because we're looking at doubling. How much time does it take to double it? So if I put 1 here, that would be 2 because that's double. Which makes us get this. And now I can do the natural log of both sides, which will make this cancel off here. And so I have the natural log of 2 equals 0.05 t. And I can divide by 0.05. Okay, so I've got natural log of 2 divided by 0.05. And there's what I get her, 13.86. Okay. Which it says round the nearest tenth, 13.9. So we're in good shape. All right, number 5. How long will it take for an investor to triple? All right, same deal here. We're going to do this A equals PERT. And if this is $1, this needs to be 3 because we're tripling it. Okay, so I have 3 equals 1 ERT, which means I can do the natural log of both sides. That makes this cancel off. So natural log of 3 equals R, which I didn't write my R in there, which is 3%, so 0.03 T. R right there, it tells us. So I can divide by it. Okay. So here, I'm going to do natural log of 3 divided by 0.03, and I got 36.62, which is 36.6, and we see we got that right over here, so we're in good shape. Okay. Number 6 here. Out-of-pocket spending in a country for health care increased between 2004 and 2009. The function, all right, here's my function. Models average annual expenditures per household in dollars. In this model, X represents the year where X equals 0 corresponds to 2004. So 2004, X equals 0. Okay? All right, this says estimate out-of-pocket household spending on health care in 2009. So in 2009, that means X would be 5. I just subtract those. So I'm going to put 5 in the equation there. So that's the same thing we've been doing here. So I'm just going to do a 2579, and then we'll do E to the power of 0.0359 times 5. And I get 30,086.08, which is around the nearest dollar, 3,086. So we're in good shape. We got that right. Okay. Now, look at part B. In what year spending reached $2,787 per household? All right, this is my f of x here. So in my equation there, I'm going to put 2,787 equals 2579 E 0.0359X. And so when I have, we'll do this a bunch, we'll have problems like this, we're going to always divide by this number right here first. So let it go away. Now this is going to make us a big old long decimal, so we'll just leave it. That way it's exact and we won't have to worry about rounding any, but I've got this. Okay. And now I can do a log since my variable is in the exponent. I'm going to do a log, which is base E, so I'm going to do a natural log, both sides. All right, this cancels that off then. And so basically what I have here, the natural log of 2787 over 2579 equals 0.0359x. And there you go, to figure out x, I'm going to divide by 0.0359. This will cancel off. X is going to equal that right there. All right, so as I punch this in, watch me now. As I do this, I'm going to do natural log. I'm going to do 2787 divided by 2579. Close it up. Okay. Then I'm going to divide by 0.0359. And this is what I get right here, 2.16, which means it's just 2 years. Okay, so let's go back up to here now. So if x equals 2, we're looking at 2006. See that? If x is 0, it's 2004. X being 2 means 2006. So it'll be 2006, which is what we got here. We got the right answer. All right, number 7. During an epidemic, the number of people who have never had the disease and who are not immune, they are susceptible, decreases exponentially according to the following function, where t is time and day. So it's going down, and you can see it is going down because my exponent here is negative. That's my k. All right, find the number of susceptible people at each time at the beginning of the pandemic. All right, at the beginning of the pandemic, that's this right here, 16,000. See, there you go. There's the answer right there. This number right here is your original amount. So at the beginning, that's it. After 5 days, okay, I'm going to put 5 in for t. So this is the same stuff we've done on these other problems. 16,000 e to the negative 0.09 times 5. I get this 10,202. And that's right there. So we're in good shape. Now the last one says the number of susceptible people after 2 weeks. All right, 2 weeks times 7 is 14 days. So I'm going to put 14 in. So we'll just keep this same equation here. Type in 14, and that's 4,538, and we got it, man. There it is. 4,538. Okay. Number 8. When physicians prescribe medication, they must consider how the drug's effectiveness decreases over time. See, when you take a pill, you have that medicine in you first off, and it's real strong, but then it tapers off. You know, your blood, it goes through your blood system, and then the potentness of it tapers off over time. And that's why the doctor gives you a pill and says take it 4 times a day. You know, you don't take it all at one time because it dissipates and it'll eventually be out of your system. So the doctor has you take it 4 times a day. This says if each hour a drug is only 80% as effective as the previous hour, at some point the patient will not be receiving enough medication and must receive another dose. This situation can be modeled with the geometric sequence. Okay, if the initial dose was 160 milligrams and the drug was administered 3 hours ago, the expression right here represents the amount of effective medication still available. Thus, this right here, that many are still in the system. The exponent is equal to the number of hours since the drug was administered, less 1. How long will it take for the initial dose to reach the dangerously low level of 20 milligrams? Okay, now, here's another thing too. See how this says the exponent is equal to the number of hours since the drug was administered, less 1. Now what that means is when you take a pill, it's not immediately in your system. It takes a while for it to get into your system, you know, until it gets digested and then distributed through your bloodstream. So that's why it's the number of hours minus 1. Okay, so that's why this is a 2 here. After 3 hours, it's 3 minus 1. Okay. All right, so we have this right here, 160, 0.8, and this is t minus 1 right here, which is your time. And what we want to do is we want to see when is that going to get down to this dangerously low level of 20. So this is what we want to solve right here. Okay? But it tells you about this being the number of hours since the drug is administered less 1. So it's t minus 1 is what this is right here. So to solve this, I mentioned this a while ago, you'll divide by this number here every time. Okay, so this goes away. So 20 divided by 160, that's 1/8. Okay, so there's where we're standing at right now. Okay, which means I'm going to have to do a log of that 0.8 base, which makes this cancel off. So let's take it over here. Log of 0.8 of 1/8 equals t minus 1. So I'm going to add 1. Which makes this go away. So t equals, now when I add this 1, I can't add it to that 1/8. I can't add it to none of these numbers up here. I just got to keep it separate. So remember now, when we type this in, I do log of 1/8 divide by log of 0.8. All right, so let's try that. Log of 1/8 divided by log of, is it 0.8? And then I'm going to add 1. It should be there at 10.31. Okay, or 10. Well, it says 10.3 right there. 10.3. Round it to the nearest tenth. Okay. Number 9. All right. The country A consumer price index is approximated by the following formula, where T represents the number of years after 1990. So here's my formula right here. And again, 1990, T equals 1. Or 0, we'll call that 0. Okay? Or we could just do subtracting, I guess, because right here it says, for instance, since A16 is about 140, the amount of goods that could be purchased for $100 in 1990 cost about $140 in 2006. Use the function to determine the year during which costs will be 90% higher than 1990. Okay, so what that means is then, if it's going to be 90% higher, it's $100 right now. So if I times that by 0.90, okay, I'm going to get $90. So it's this much higher, which means it's going to be 100 plus that. So we're looking at it being 190. So if it's going to be 90% higher, that means it's going to be $190. And that's my A sub t. Okay, which means right here in this equation, I'm going to put 190 right there. And that's what I'm going to solve. Okay, so again, what this says now, okay, basically, A of 16 is about 140. So if I put 16 in, I'll get 140. That's the amount of goods could be purchased for $100 in 1990, costs about $140 in 2006. So here, I punch that in and show you what I'm talking about. 100 e to the 0.021 times 16. And you can see there $140 right at it. Okay. It says use the function to determine the year which the cost will be 90% higher. So I do 90% times the original $100, which would be $90 higher, which would be $190. So that thing that sold for $100 in 1990 is going to sell for $190 now. In what year? All right, so put that in. Okay. So now I'm going to divide both sides by 100. Which this cancels, it would be 1.9 equals e to the 0.021t. And then I'm going to do a natural log to make this cancel out. And so natural log of 1.9 equals 0.021 times t. And now I'm going to divide by 0.021. This will cancel off, and t equals, all right, let's see here, natural log 1.9 divide by 0.021. And I get this for 30.56. So 30, if it's 1990, add 30, that's 2020. So 2020. Now notice here it says round down. I didn't explain that, but see, look here. We'll let it write down. But this is 30.56. Okay. I wouldn't round it to the next year, because see what that means? It's in the middle of the year. See, 30.99, that's still in the 30th year. It's not till it goes over to 31.0, then it's 31 years. But this is 30 years. 30.56 does not round up. We always round down because it's during that year. So if I add 30 to 1990, I get 2020. And that's the year that this will be 90% higher. Okay, number 10. Okay, number 10. Sales of a product under relatively stable market conditions, but in the absence of promotional activities such as advertising, tend to decline at a constant yearly rate. I had somebody ask me why they had a commercial on TV, because everybody knows them. I can't remember what item it was, like Pepsi or something. Why does Pepsi put that commercial on there? Everybody knows who Pepsi is. Why do they need to put this commercial on there? Well, because if they don't, their name will decline. People need to be constantly told about things, you know, and so they'll keep buying their product. If the rate of sales decline varies considerably from product to product, but seems to remain the same for any particular product. The sales decline can be expressed by this function right here. So here's my sales decline, and you can see A is negative. It's declining. In this formula, S sub t is the rate of sales at time t measured in years. S sub 0 is the rate of sales in time t equals 0, and A is the sales decay constant. All right, so what that means is A is the rate at which this is declining, and S sub 0 is the original amount. S sub t is the amount after t years. So it tells us right here, if A is this and S sub 0 is this, find the number of years it will take for sales to fall to half the initial sales. So we're going to find the half-life. Okay? Which means if this original was 2, then that would be 1. It's half. So let's do that. 1 equals 2e to the negative a was 0.18 t. And that's how you set it up. Divide by 2, and then when I do that, see I get 1/2 over here. Okay, and then solving this just like we've done the other ones, I'm going to do natural log of both sides, so this will cancel. So coming over here, we'll have natural log of 1/2 equals negative 0.018 times t. And then we'll divide that at negative 0.018. This will cancel off. I got t equals that right there. So let's see here. I got natural log 1 divided by 2, 1/2. And I'm dividing that by negative 0.018. I get this 38.5. Well, look at me here. I messed up. I added a 0 in right here. You see that? There's no 0 here. So let me change that. Made a mistake. Added a 0 in. So if I take that 0 out, there's we get 3.85. This is rounded to the nearest tenth, which is 3.9. Let me see my answer right there, 3.9. Okay, you gotta be careful by adding zeros and stuff in like I just did there. That was a dumb thing. So you got to be careful about doing stuff like that. Number 11, suppose at a certain area the consumption of electricity has increased at a continuous rate of 10%. If it continued to increase at this rate, find the number of years before 3 times as much electricity would be needed. Okay, so we're going to do the same thing. A equals A sub 0 e to the kt. This is 10%. It's increased, so that's positive. And then we want 3 times as much. So if this is 1, this would be 3 over here. If it started at 1, it would be 3 higher. So, you have to have the 1 there. And so now all I need to do is the natural log, both sides. This will cancel. So natural log of 3 equals 0.10 times t. And I'm going to divide by 0.10. Alright, so I got natural log of 3, close it up, divide by 0.10. And I got here 10.98, which is, it says around nearest to the nearest tenth, which would make it go up to 11. So we got it right there, 11. Okay, 12. All right, 12 is a little bit of a problem, causing some people to kick themselves. All right, it says evaluate these. So I'm going to put 20 in for X. I'm going to put 65 in for X. This is as age increases, so does the likelihood of a particular disease. The fraction of people X years old with the disease is modeled by this right here. So here's my model. And that makes sense. Like heart disease, how many 12-year-olds have heart disease? How many 24-year-olds have heart disease? How many 36-year-olds have heart disease? How many 48-year-olds have it? How many 60-year-olds have it? How many 72-year-olds have heart disease? As the number gets higher, more and more people start having heart disease. So as age increases, so does the likelihood of this disease. So basically, I'm just going to put this 20 in there. Now when I do this, all this will have to be in the bottom. It'll have to be in parentheses. Okay, so when I type this in, I got 0.9 divided by, and I'm going to have to have parentheses there. So 1 plus 267 e to the negative 0.122, and I'm putting in 20, so times 20. Okay, and then there's my parentheses, and I got 0.037. Okay, and I believe you see our answer right there. We're in good shape with that. Okay. And then 65, I'm going to do the same thing. I just got my equation on there, so I'm just going to go type 65 right there, and then there you go, 8.821. Okay. Okay, I think we're answering the wrong one. I think it needs to be down here in B. This is 0.037. This is 0.821. Okay, round 3. This means that among people age 20, okay, 3.7% have the disease. See, this was not reading right, the A one wasn't, because it said 20%. It's supposed to be people age 20. So 3.7% have the disease, while people age 65, it's 82.1% have the disease. Okay. All right, now part B. At what age does the likelihood equal 50%? Right, so what I'm going to do there, I'm going to let this f of x right here be 0.50. Okay. So I have to take this equation, I have to solve it for x right there. Alright, so follow closely with me on this, okay? What I'm going to do, since x is down here in the denominator of this thing, I'm going to multiply both sides by this whole denominator here. 1 plus 267e negative 0.122x. 1 plus 267e to the negative 0.122x. And that'll cancel off both sides there. Cancel off over here on this side. And it puts it over here. So I've got 0.50 times this. Alright, so what I can do then, I've got this times 0.50. Okay, now I can distribute that, but with this having the exponent, I could probably make a mistake. So I think what I'm going to do is I'm going to divide by 0.50. And let me write it out again here. 1 plus 267e negative 0.122x equals times 0.50, and write it on there, equals 0.9. So I'm waiting on doing this dividing thing. Let me just write it out first. Okay. Now, like I said, I can distribute that 0.50 into here, but I think I might just go ahead and do divide by it, which makes this cancel off, and I got this right here. Okay. 1 plus 267e negative 0.122x equals, and this is going to be 0.9 divided by 0.5. Okay, that's going to be 1.8. So I'll go ahead and divide that since it divides real easy. And now I'm going to solve this, which means I'm going to minus 1 on both sides. So 267e negative 0.122x equals 0.8. Okay? Alright, then right here I'm going to divide by 267. That makes this cancel off. And I don't know if that's going to divide very good, so I'm just going to leave it. Okay. And now I've got e to the power of, with my x in it, I need to do a log, which is natural log, because that cancels e. So I've got negative 0.122x equals natural log of 0.8 divided by 267. And then I'll divide by negative 0.122. This will cancel, and then I'm going to type all that in. So basically, I just go natural log. Can you see on the screen there? Okay. We do natural log. I'm going to have 0.8 divide by 267. Close it up. And we'll divide again by negative 0.122. And that's what I get right there, 47.62. It says round to the nearest integer, so that'd be 48. And look here, man, we got it, 48. That's the right answer. Okay. Moving on, number 13. Student enrollment in the city school district has projected growth as shown in the graph here. So here's where we're at in 13-14, and here's where we're at in 23-24. All right, use this model right here, like we've been talking about this whole section today, to find an exponential function that gives the projected enrollment y in school year x. Let the school year 2013-14 correspond to x equals 0, and 14-15 is x equals 1. So, all right, now this is kind of confusing here. We got 13-14 is x equals 0, and then 14-15 is x equals 1. Okay, and so on. Okay, so starting this out, 14,240 is our original amount. So that goes in the box right there. And I've got E, and I need to figure out my rate. All right, so the way I do this is, I hope I can explain this good enough. Okay, I've got to take these 2 points right here, or take this point right here rather, take this one and put it in to figure out what my rate is. Because see, I don't know my rate, so I'm going to take these numbers for x and y. If 23, 24, that means right here, if that's 13, 14, that's 10. X equals 10. So what I'm going to do is I'm going to put 10 in for x right there. Okay? And I'm going to put this 19,910 in for y. So it looks like this. And there it goes. So what I'm doing here is, sorry, didn't have it on the screen. So I'm putting the 19,000, see from the graph here, I'm taking this point right here, 19,910, which happens at 23, 24, which means x equals 10. So I'm putting 10 in for x right there. I'm putting that 19,910 in for y. And so it looks like this. Okay? And then we'll solve and figure out what the k is. That's what I got to have in this box right here. So I got to divide both sides by 14,240. This cancels off. All right, now as I've told you before, I'm going to leave this. It's probably best to just leave this and divide it and stuff later, but I've got this. Okay. Which means now I'm going to do natural log of both sides because that'll cancel off my e. So that means the natural log of 19,910 divided by 14,240 equals 10k. And now divide by 10. And then k is going to equal this. Okay? So I'm going to type it in. So I'm going to type in here natural log, and I'm doing 19,910 divide by 14,240. And I'm going to divide again by 10. And I get 0.033516. Where does it say it at on here? 3 decimal places. So we want this right here. The 5 makes the 3 go up to a 4, so 034. And there you go, man. We got that right. I got that right. This is estimate the school year for which projected enrollment will be 22,000 students. Okay. So what that means is I'm going to take this equation here I just built. Y equals 14,240 e to the 0.034x. And so this is asking what year will it be 22,000. So if this is 22,000 right here, okay, that's what we're doing. So I divide by this 14,240, which makes this cancel. And so I'm going to leave this, like I've told you before, we're going to leave this. That equals e to the 0.034x. Now I've got my exponent in my variables in the exponent, so it means I'm going to have to do a natural log of both sides to cancel this off. That means I got the natural log of 22,000 divided by 14,240 equals 0.034x. And then divide by 0.034. And x equals that right there. Okay, so typing this in, natural log 22,000 divided by 14,240, close it up, and divide again by 0.034. I get 12.7937. Okay, and okay, it says round up to the nearest school year. All right, so that's going to be 13. So x equals 13. All right, which means right here. If I add 13 to this, that's going to be 26. Add 13 to that, that'd be 27. There you go. That's the school year, 26, 27. Which is right. You can see that down here? We're right. This is really hard to explain just on a video here. I don't know if you understand it or not, but call me or something if you need help. And here's another one similar, and this is the last question, okay? And then we're closing off. In 2000, the population of country A reached 4 million. And in 2025, it's projected to be 6 million. Find the values for P sub 0 and A so the following formula models the population of country A near X. So here's the same thing we just did. Okay. All right, so in 2000, it was 4 million. So there's my P sub 0. So f of x equals 4. A to the x minus 2000. All right, so since that's 4, that's the original amount, we put that right there. Okay? All right, so now we need to figure out what, I guess we need to figure out A now. So what I can do, I can figure out A by taking this other one here. See, in 2025, it's projected to be 6 million. So that means right here I'm going to put 2025 for x. I'm going to put 6 over here for the function of x. So it looks like this. Okay, 2025 minus 2000 is 25. All right, so divide by 4 on both sides. That's going to be 6 divided by 4 is 1.5. That's a good decimal, so we can leave it like that. All right, then I'm going to do 1 over 25 power, which makes this cancel off, and A equals, all right, let's do this here, 1.5 to the 1 over 25 power, which is this right here. And I think we round it 5 decimal places. 1, 2, 3, 4, 5. All right, after that we got a 0, so there you go. That's going to be 0.01635. That was 4. And look here, man, we're in good shape. Okay. Now, what would the population be in 2010? Now, here's what we got. Since I've got this as A, and I've got 4 is the P sub 0, I've got this equation right here. F of x equals 4, and then A is 0.01635 to the x minus 2000 power. So there's my equation I got from what we just found. We found this number and this number. Okay. All right, so estimate the population in 2010. So if I put 2010 right here, I can just punch that in. 4 times 0.01635 to the 2010 minus 2000 is 10. That'd be 10 power. And I have this right here. Okay. Something doesn't look right there. Okay, something's not looking right. I put 2010 in right here. minus 2,000 is 10, so 4 times this to the 10 power. That's what I did, and that's not what the answer is. Let me go back. Yeah, look here, there's a 1 in front of this. See, I just realized there I didn't have my 1 on there. Okay, I've circled this, but I don't have, see, that was a 1, I didn't write it down. So let's go back to this then. There should be a 1 right there, and that'll make the world difference. So I left that 1 off. I can't see when I'm doing this. There's a big old glare on the calculator and everything. But there it is right here, 4.7. That's what the answer is. 4.7. You see it right here, 4.7. So it's going to be 4.7 million in 2010. Then part C says the country's population might reach 11 million during what year? So that's my f of x. So that means I'm going to put 11 over here for f of x equals, this was 4, this is 1.01635, and this is the x minus 2,000. So basically I'm going to put 11 here, and I'm going to solve x, which means I'm going to have to divide both sides by 4. This cancels off, so this is going to be 11 over 4. Now that's 2.75. Okay, and now we've got our x and the exponent here, so that means I'm going to have to do a log of this base, 1.01635. Log of that base, 1.01635. And this will cancel off here. So log of base 1.01635 of 2.75 equals x minus 2,000. And so I'll add 2,000. And that's x. Alright, so remember when you do logs like this now, we hadn't done these for a while. I'm going to do log 2.75, and I'm going to close it up. Okay? Get where you can see it. I'm going to divide by log of the base, which is 1.01635. Alright, then I'm going to add 2,000. 2,062. That's what year, and you see the answer down there, we're good. That's what year the population would get to 11 million. Okay. Well, I know this is kind of rough, man. It is for me because I can't see you guys. I can't really tell if you're getting this or not. I'm trying my best, but if you need more help, contact me and I'll help you all I can, all right? So have a great rest of the day. Bye-bye.